In Lab 3 of Physics 2212, we experimented on circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel. Multimeters are used to measure the actual values of conventional current and potential differences in the circuits. The behavior of ohmic resistors and capacitors are also examined. We found that the current in a 2-resistor circuit is 0.02 amperes and that the calculated and experimental values of current and potential difference are similar. In an RC circuit, the greater the resistance of a resistor, the longer it takes for the capacitor to charge and discharge. The time constant was found to be 6.002 seconds. Important concepts in this lab are the node rule, loop rule, and Ohm's law. The node rule states that the sum of the currents entering a node is equal to the sum of the currents flowing out of the node. The loop rule states that the difference in potential for a path that results in a round trip is zero. Ohm's law can be used to determine electrical resistance. Here are the formulas for the three important concepts used in this experiment. In this experiment, several different circuits were created. The system is the ammeters and voltmeters, while the surroundings is the circuit. In the first circuit, two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters were used. By using the loop rule formula, the calculated current was found to be 0.0204 amperes. The actual current, as depicted on the ammeters, is 0.02 amperes. Reversing the ammeters results in the same current. In the second circuit, an ammeter is replaced with a voltmeter. The calculated potential difference is 3 volts, which was determined from the two batteries. The calculated current is 0 ampere as the voltmeter has high resistance. The actual values according to the model are the same. By closing the previous circuit, the potential difference between the points shown in the top image can be determined by using a voltmeter. The potential differences are shown. The loop rule is supported as the sum of all the potential differences is equal to 0. In the third circuit, an ammeter is added parallel to the 100 ohm resistor. The current increases to 0.06 amperes due to the current being split at the node between two paths. The experimental values can be used to calculate resistance. By using Ohm's law, we determine the electrical resistance of each part of the circuit. They are shown here. In the fourth circuit, a 9 volt battery, 10 ohm resistor, and 200 millifarad were used. Using a stopwatch, the charging and discharging time can be measured. The charging time when there is a 10 ohm resistor is 15.2 seconds and 25.6 seconds when it is 20 ohms. The discharging time when there is a 10 ohm resistor is 14.9 seconds and 27.2 seconds when it is 20 ohms. To determine time-dependent voltage, the 10 ohm resistor is replaced with a 30 ohm resistor. The battery is removed and the capacitor is discharged. The potential difference is recorded every second for 20 seconds. It is then plotted on a graph and the slope can be used to solve for the time constant. The slope is negative 0.1666 and the time constant is 6.002 seconds. We found that the calculated values are very similar to the experimental values. Possible errors include timing errors when measuring the potential difference and rounding errors when doing calculations. If a real ammeter was used, there would be changes in resistance. Unlike the model, real ammeters have some resistance and the current will be decreased. The ideal model predicts that the capacitor will reach full charge almost instantly. This cannot happen in real life as wires and capacitors have resistance.